Hey chemists, how you going? So basically this video is going to start covering the concept of chemical equilibrium. This is, I guess, a three-part series, and the first part is going to be looking at the concept of equilibrium and graphing. So this is designed to go along with your equilibrium notes. So have them alongside you, follow along, and try to take notes where you can. So let's get into this one. So what is the concept of equilibrium? So the study of reaction kinetics is what we did previously in our subtopic 2.1, which is rate of reaction, and that's looking at how fast a reaction occurs. So how quickly do those reactants turn into products? So we're talking about if you change certain reaction conditions, you can make the reaction go faster or slower. The study of equilibrium is a different lens on which we're viewing this. So this is how far can the reaction occur. So that's kind of the framing of this concept. So what do we know already? We know that the equilibrium arrow exists. We've seen this equilibrium arrow before, and we probably know that that indicates that you've got two reactions happening there. So you've got a forwards reaction, which is indicated by this kind of bottom part of this arrow, where you've got the reactants turning into the products. And then you've got the backwards reaction with the arrow at the top, which indicates that the products are turning back into the reactants. So your acetic acid and water is ionizing, and then those ions are turning back into the non-ionized form. So in terms of the acids and bases topic, that's probably where you saw those arrows before. So you're talking about strong and weak acids, two-stage, three-stage ionizations for diprotic and monoprotic acids. So I guess when we were looking at topic 1, we were looking at things like acid rain, and photochemical smog. So acid rain is probably the main one. You've got that sulfuric acid and that nitric acid that are ionizing. Sulfuric is a diprotic acid, so you've got that two-stage ionization. Anyway, I'm kind of going a little bit off topic there. Not off topic, but off track from this. So the single arrow shows reactions that go to completion. Most of the reactants are used to make the products. So in this case, silver and chloride ions, single arrow, forming our silver chloride. That's indicating that pretty much all of this is going to go to this. There might be some left over, but basically that's a one-way reaction. It'll end at some point, and then we're done. The double arrow is reactions that do not go to completion. They're reversible reactions. Some of the products react to give back the reactants. So basically what I was saying before. And a good example of this is the Haber process in order to make ammonia. So this is a commercial process, basically taking atmospheric nitrogen, adding hydrogen, high temperatures, we're making some ammonia. But some of the ammonia turns back into the nitrogen and the hydrogen. Now, I won't play this video, but I'll have it in the lesson for you to view. This is a great example of chemical equilibrium. Just a way to explain and mechanize it. I'm kind of doing the reactions because I've just watched the video. Look, I won't spend too much time on it, but check this video out, it explains equilibrium really well. So what is equilibrium? The old assumption, for all reactions, every single reactant molecule collides. It reacts and converts into 100% of the products. Is this a reliable assumption? And we'll find that it's not. Many reactions do go to completion, so the reactants almost convert completely to products. But there are many chemical reactions that do not reach completion. There's no end to them. So what's happening in both these types of reactions, and how can a chemist tell the difference? So we can maybe talk a little bit on a molecular level, but if you're there in the lab, how can you tell what's going on here? So given the right conditions, reversible reactions will eventually reach a balance between the conversion of reactants into products and the products back into reactants. And this balanced state is called equilibrium. So we want to think of the concept of equilibrium as a bit of a balance. The reaction seems to stop at equilibrium. So to the naked eye, it seems like nothing's happening anymore. So basically the concentration of reactants and products is remaining constant. But in reality, this is not a static state, but a dynamic one. We all remember being in the lab and you might add some metal to some acid and it fizzes and there's smoke and then it's done. That's an example of a one-sided reaction where you're going to get completion, but some of these equilibrium reactions, it might look like nothing happens, but there is actually something going on a molecular level. So chemical equilibrium is considered a state of dynamic balance in which the rates of the forward and reverse reactions are equal. So that red is quite important. So the rate of the forward and the backwards reaction are equal. There's no net change in the concentration of reactants or products while in a system that's at equilibrium. So this slide basically summarizing that again, the rate of the forwards and the backwards reaction is equal in a state of equilibrium. So the forward reaction is converting reactants into products just as fast as the back reaction is converting products back into reactants again. The right amount of the amount of reactants and products stays the same overall. The individual molecules are still converting between the two. So there's still something going on, okay? But because it's happening at the same rate, to the casual observer, I guess, it seems like nothing much is happening because the concentration isn't changing. So that, therefore, we can describe it, and that might be a tiny bit cut off there, but it's a state of dynamic equilibrium. So it's characterized by the following features. The macroscopic properties remain constant. So macroscopic means what you can see to the naked eye, but on a microscopic scale, looking at the individual atoms, there's continual change. This is only possible in a closed system, which means a system that isn't allowed to have external forces coming in and acting upon it. So basically, if we had a reaction and you were able to pour in some water or another chemical was able to be added, that's not considered a closed system. So you might want to visualize it as a bit of a box or something like that where there's no ability to change. And equilibrium can be attained from either direction, forwards or backwards. I've covered this, the fact that the macroscopic properties remain the same. So the color remains the same, the concentration remains the same, the pressure and temperature as well. On a microscopic level, there's particles reacting in a forwards and a reverse direction where the rates of those are the same. So the closed system, energy but not matter can be exchanged with the surroundings. So energy, we're talking about things like heat, but matter, we're not allowed to add or take any matter away. So an example of an open system is acid and a metal, and then you have hydrogen gas coming off. The fact that the gas would be escaping means it's not a closed system. So this is how I would maybe, or a bit of an analogy for dynamic equilibrium. I don't know if you've ever done this before, but a person running up an escalator that's going down. So basically, the rate at which this person is running up would be considered the same as the speed of the escalator going down. So if you were someone observing from a long way away, so that kind of macroscopic observer, it might appear that this person is just kind of not moving at all. But if you come up close, so say the microscopic level, you can see that this person is moving, he's jogging up the steps, and the escalator is moving downwards. So there might seem like there's no progression, but really there is two separate things going on here, that forwards and backwards reaction happening. Dynamic equilibrium can occur in chemical and physical systems. So chemical, we've given an example of the Haber process. Physical, ice melting, so this is a bit of an interesting one. At 0 degrees Celsius, water exists in both the solid and liquid phases. There's a balance between the rate of solid ice melting and liquid water freezing. So yeah, you basically got two things going on there between that solid and liquid state. So that's another example of some dynamic equilibrium happening. The position of the equilibrium. So this indicates whether reactants or products are favored, whether the forwards or backwards reaction is preferred. So this is starting to go into a little bit of the next concept. So for a single reaction with only one arrow, with a full arrow, the equilibrium favors the product. So what that means is when you put these together, you're going to make the product. With this one, we can say that the equilibrium favors the formation of the reactants. So when you've got these, this reaction happening, there's actually more of the backwards reaction happening than the forwards reaction. And we know this from experimentation, and this is different for different reactions. We're going to go into this a little bit more depth in video 3. So now we're going to have a look at a few equilibrium graphs. So here, not the best graph in the world, but we've got the rate of chemical reaction and the reaction time. So you can see the forwards and backwards reaction, they're kind of mirrored in terms of what happens. So the forwards reaction, at the beginning of the reaction, the rate of reaction is very high because there would be no products in this reaction, I guess. You can see the products would be 0 down the bottom. And then the reaction starts to happen, and then the rate would decrease. As the reactants are forming products, that means there's less reactants, which means the rate of reaction will slow, and that gets lower. The opposite happens with the backwards reaction. As there's the formation of product, there's more product to turn back into reactant, so this will increase. And then this will happen until they match up. And when there's a slope of 0 for the rate, that means that the rate is stabilizing. It's no longer changing. And we know that when the rate of the forwards and the backwards reaction are the same, then you've reached that state of equilibrium. So basically, for an equilibrium graph, when there's a flat line, that means that you've reached equilibrium. So that's probably something that we're looking for here. So as I mentioned before, how do we know if a system has reached equilibrium? It's when the rate of forwards equals the rate of backwards, when there's a constant temperature, constant pressure, constant concentration, constant color intensity, and there's still a reaction going on, but there's no change. I feel like we've covered that a few times now. So let's look at a couple more graphs to finish off. So here we've got the concentration. So not rate of reaction this time, we're looking at the concentration. And remember, when we reach equilibrium, then that concentration remains constant. So the difference between this graph and the last one is we don't need them to match up, okay? You can see that the change is equal but opposite. So as the concentration of the reactants, which is high at the beginning, decreases, the concentration of the products increases with the same intensity, they're just opposite. So positive, negative slope. They'll cross over. And then it gets to this point, this dotted line here, where that slope evens out and goes to a slope of 0, which means that we've reached dynamic equilibrium. So essentially, at the equilibrium point of this reaction, the concentration of products is greater than the concentration of reactants. They don't need to be the same all the time. Here's another one. Very similar, reactants, products. You can see equal but opposite in terms of their slopes when this reaction happens. When we get to this point, for me that dotted line could be about here, but that's okay. You can see when the slope is 0, then this reaction has reached that dynamic equilibrium. Here's another one. So we've got reactants and products, and very similar, increase, decrease. Actually, now that I look at it, it's not very similar. So what's the difference between these graphs? The difference that I can see is, yes, this one goes up and this one goes down, but the steepness of that slope is different. So if I was to measure the difference between here and here, if I was to draw a line, let me just try and get my pen tool here. If I was to draw a line, or triangulate that, and I have this distance, and I compare that to the distance on the red line, here and here, we can see, is that about twice as much? About that compared to that? Looks like twice as much. So what does this tell us? That tells us that the mole ratio between those is a 2-to-1 ratio, okay? So, and we can see that from the actual reactants and products. You'd have 2 of these turning into 1 of these. So basically that lets you understand why that concentration is different. Because as this goes up, this goes down, and the ratio is 2-to-1, so you need 2 of these for every 1 of these. But same concept, you reach that dynamic equilibrium. at a certain stage when that curve flattens out. So one more here. This time we've got 3 reactants and products. So what can we glean from this graph? This does say time on the bottom. I apologize, that's cut off. So which one is the reactants and which ones are the products, I guess? So the green SO2 goes down, this one goes down, this one goes up. So that tells us that we've got 2 reactants and we've got 1 product, okay? So in terms of us writing this chemical reaction, it would be O2 plus SO2 goes to SO3. And then we would balance that 2, and that's balanced. So the mole ratio is 1 to 2 to 2. So what that means is the steepness of this slope should be half as the steepness of this slope and the steepness of this slope. Now, in terms of if I wanted to measure that, I would be, again, kind of triangulating that as much as possible. So the yellow SO3, and I'd be measuring that with a ruler. The green SO2, you can see that they are the same, and they should be. SO2, SO3, it's 2 and 2, so it's the same. But then you're looking at the brown O2, and you can see that that steepness is half as the other ones. So basically, if you weren't given that equation and you needed to work something out yourself, you could work out the mole ratios based on the graph. And again, reaching that point of dynamic equilibrium, and at equilibrium, the concentration of SO3 is greater than SO2 and O2. And if you kind of combine those two, you'll probably get to something similar to SO3. So the last one here, so it's the same reaction, but here we started off with SO2 and O2 and no SO3. And this one we started off with SO3, but no SO2 and O2. So the curves are flipped, I guess, and you end up reaching that dynamic equilibrium. So now you've got a couple of tasks to try on your notes. So what I want you to try with this one is to draw your own equilibrium graphs. So this reaction here is reactants and products, and the mole ratio is 1 to 1. Wherever you start is up to you, but you need to make sure that the mole ratio of 1 to 1 is represented accurately, which means the difference between the start and the finish is the same. And because you've got reactants and products, as one goes up, the other must go down. So try to draw that. When you're drawing, it's really hard for me with this pen tool, but I would recommend starting somewhere, finishing somewhere. The flat line would go after here. So then you need to have kind of like a nice curve here. I'll draw a bad curve. Why is that a bad curve? With the rate of reaction in terms of concentration, the initial rate of reaction is fast, and then at the end it slows down. So this is a poor curve because that slope doesn't accurately represent a fast rate of reaction and then a slow rate of reaction. So if I was to do it again, and I was to do it better, you would have a steep rate of reaction. That's actually bad. That shouldn't go in like that, but that's okay. Where it goes fast initially and then flattens out. That's actually really bad. I'm going to try it again. Here, here, and you go steep and then you flatten out like that. So that's a little bit better. It takes a bit of practice. Obviously, I need my own practice for that. Oh, I'm giving you the answer. Skip, don't pause that. Okay, and then this one as well. I might just cheat a little bit and move forward in my PowerPoint without showing you guys the answer for this one. So this one, the difference is the mole ratio is 2 reactants to 1 product. So how do you demonstrate that? You need to show that difference in terms of that concentration. So guys, thanks for watching video 1. Really appreciate it. Hopefully that helped you understand a little bit the concept of dynamic equilibrium. And I'll see you in video 2.